Hello everyone, welcome. This is paper 2 from May 2025 and this is time zone 2. Let's have a look and see what we can do. Question 1. Tie cushions are designed with a triangular cross-section and are made from layers of smaller cushions. These cushions can be modeled as triangular prisms. This is shown in the diagram. So here we have a whole cushion itself. It's made up of these triangular prisms, and this is a cross-section, that is to say a two-dimensional cross-section or kind of a slice through the pillow itself. What would that look like? There's this cross-section right here. Part A asks us to write down the number of triangular prisms in the bottom layer of a cushion with 4 layers, and then for part 2 with 5 layers. So essentially they're asking us, if we have some cushion, how many triangular prisms are there in this case, the 4th layer, or in this case, the 5th layer. We can go ahead and find a pattern, but since it's a small number of triangles in this case, let's go ahead and just count them. So here's the 4th layer. We have 1, 2, 3, 4, 5, 6, 7, in this case, 7 triangular prisms. So we switch colors. And if we're asking a question about the 5th layer, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9 triangular prisms. All right. So we can go on and actually find a pattern in this case, but I think that's actually what they're going to ask us in the second part. Mayumi notices that the number of triangular prisms in the bottom layer of the cushions forms an arithmetic sequence. Part 1 of B asks us to write down the common difference of this sequence. So the common difference for an arithmetic sequence is the value that we need to add or subtract to move from one term to the next. So in this case, the term number refers to the layers. So term 1, 2, 3, 4 is layer 1, 2, 3, 4. And the value of the term is just the number of triangular prisms. So let's look at the number of triangular prisms in each of these layers, and then we'll find the common difference. So in the first layer, there's 1 triangle. In the second layer, there are 3 triangles. And then in the third layer, we have 1, 2, 3, 4, 5 triangular prisms. And then in the 4th and 5th layer, we already found that this was 7 and 9. So now the question is, okay, we've got this sequence, 1, 3, 5, 7, and so on. What is the value that we need to add or subtract to go from one term to the next? In this case, it's 2. We add 2 to go from one term to the next. And that would be our common difference. So in this case, the common difference of the sequence, D, is equal to 2. All right. Part 2 of part B. Find an expression for the number of triangular prisms in the bottom layer of a cushion with n layers. So what they're asking us to do here is generalize this sequence. So what happens if we want to know, let's say, the number of triangular prisms in, let's say, the 6th layer, or the 10th layer, or the 50th layer, or the nth layer, any layer, for example. Instead of just adding 2, can we create a formula that allows us to substitute the term number or the layer number and find out how many triangular prisms there are in that layer? And we can. For that, we'll use our arithmetic sequence formula. So this is in our formula booklet, and actually you can go and bring it up. Here it is. Maybe I'll actually erase these parts and go over this. So in this case, un is the value of a given term, in this case, how many triangular prisms. U1 is the value of the first term, n is the term number, what we would substitute in a situation, and d is the common difference. Really, we're interested in finding d and u1. If we have those two ingredients, then we can write a formula. So let's go and write that out and see if we can substitute. So un is equal to u1 plus n minus 1 times d. U1 is the value of the first term, in this case, the number of triangular prisms in the first layer, and that equals 1. Plus n minus 1, n is just a term number, we leave it as it is, and d, the common difference, is equal to 2. We found that right here. So this is actually okay. We can leave our formula just like this. If we wanted to, we could expand. So 2 times negative 1, 2 times n. And so we would have something like this. 1 plus 2n minus 2 times negative 1 is negative 2. Now we have 1 plus negative 2, or negative 2 plus 1 is going to give us negative 1. And altogether we would have 2n minus 1. But you can actually leave it like this, and that would be perfectly fine as well. The IB would not mind in this case. So here's our answer, or here's our answer. And it links un to the term number, or in this case, the layer. Okay. Moving on. Mayumi wants to extend this design to create a cushion with 9 layers. Find the number of triangular prisms in the bottom layer of Mayumi's cushion. Okay. So she wants to create a cushion with 9 layers, and the question is, how many triangular prisms would there be in this 9th layer? So we have a formula, that's what we found right here, this nth term formula, which tells us the number of triangular prisms for any given layer. So let's use this essentially as an input-output function, or a function where we can input and find the output, to find the number of triangular prisms that would be in the 9th layer. So in this case, the layer is n, and it's equal to 9. And what we want to find is u9. What is u9? So wherever we see n, let's replace it with 9. We have 2 times 9 minus 1, which will be 18 minus 1, or 17. So in this case, we would have 17 triangular prisms in the 9th layer. Once again, here's a function which relates the layer to the number of triangular prisms. They told us the layer is equal to 9. Substitute in that value of n, and then we can find the number of triangular prisms, 17. All right, part 2 of part C. Calculate the total number of triangular prisms in Mayumi's cushion. So this is an interesting question. It's nice of them, I think, in a way, to highlight this word total, because now we're not dealing with just a term number, we're dealing with the sum of n terms. So in this case, calculate the total number of triangular prisms in this cushion with 9 layers. So not just the 9th layer, but all of the triangular prisms. How many triangles are there essentially? For this, we'll need to use our sum formula. So let's go to our formula booklet, and we'll find the sum formula here. So we want to find the total. Here's the sum right here. Sum of n terms is given by n over 2, 2 times u1, the first term, n, the term number, and then d, the common difference. This is the equivalent formula, but for this we need n, u1, and we also need to know the value of the 9th term. In this case, we actually do know this, and this, so this might be the easier formula to use. Both of them will work though. Okay, so let's write it out. Where can we write it? I'm actually going to move this a little. This I think we can delete, but this I'll move over, and I'll use this space here. Okay, so what's our formula? Sum of n terms is equal to n over 2, u1, value of the first term, plus un, value of the nth term. In this case, we want to find the sum of the first 9 terms. Wherever we see an n, we'll replace it with 9. So n, in this case, the number is 9, number of terms, number of layers. u1, value of the first term, is again one triangle in the very first layer, plus 17 triangles in the 9th layer. So remember, u9 is 17. Okay, let's go on and complete this. What can we do? Let's write this out. 9 over 2, and then this is 1 plus 17 is going to be 18. And now, what can we do? I'm going to write this horizontally just because I'm running out of space. Usually, don't really like to so much. But if we have 9 over 2 times 18, I hope this isn't too much of a stretch in some ways, but we can say 9 over 2 times 18 over 1. And then remember, 18 over 2, this would become 9, this would become 1. And now we have 9 times 9, multiplying both numerators, becomes 81. And then 1 times 1 is just 1, so we can leave it as 81 over 1 or just as 81. So in this case, there are 81 total triangles in a cushion with 9 layers. And if you wanted to be honest, you could actually go and just put this into your calculator, and that would be fine as well, and you'd get the same answer. Okay. Question D. Find an expression for the total number of triangular prisms in a cushion with n layers, giving your answer in its simplest form. Okay. So this is an interesting question because we want to, in a similar way as earlier, where we wanted to find a general expression to find the number of triangles in the nth layer, here we want to find an expression for the total number of triangles for a cushion with n layers. So since we're dealing with total numbers, we want to use the sum formula. Remember we had two sum formulas. Let's go back to those just for a sec. So here we are. Two sum formulas. Which one should we use? Remember the difference between these two formulas? This one required us to know the value of the nth term, the value of the final term. If we want to generalize and create a formula that's going to be useful for any situation where we have n number of terms, we're not always going to know, let's say, the value of this final row, the number of triangles in that final row. We're not always going to know the nth term. Since they ask us in the question to write it out in terms of n, this is going to be the more appropriate formula because it's terms of n, d, and u1. And we know what u1 is and we know what d is, but we don't always know what this un is. So that one's not going to work for us. We'll have to use this one right here. Okay, so let's write that out, and I think there's enough room here. So let's write it out here. Sn is equal to n over 2. This was 2u1 plus n minus 1 d. And this was in the formula booklet, once again. I'm actually going to move this over just because running out of space a little. Okay, so now we want to generalize this for n. So Sn is equal to, we don't know what n is. It's going to be in terms of n. So we can leave the n as an unknown. N over 2 times u1. We do know what u1 is. u1, once again, was equal to 1. It's the number of triangles in the first row. Plus n, again, we don't know. And then this is times d, the common difference, which was 2. All right, now let's try to clean this up a little because they're asking us in this case, simplest form. Here, in this question, they didn't ask us to write it in simplest form, so this would have been perfectly fine. Here, if they asked us to write it into simplest form, then we would actually need to simplify and expand and so. So that's what we need to do here. So let's go. N over 2. 2 times 1 is just 2. Plus, and now we have n minus 1 times 2. So we're going to need to expand. So 2 times negative 1, 2 times n. 2 times n is just 2n. 2 times negative 1, this last part here, is going to be negative 2. So just to maybe go over this a little more, this n minus 1 times 2 is the same as 2 times n minus 1. Essentially, a times b is the same as b times a. So although when we do expansion, we often have this coefficient in front, but really if we want to use what's called this rainbow method, we can do this in the same way, whether this coefficient, this just plain number, is at the back, or if it's at the front. That's because multiplication is what's called commutative. It doesn't matter the order that we go in. So Let's go ahead and clean this part up. We have 2 plus 2n minus 2. So now let's group like terms. Here we've got a plain 2 and a negative 2. 2 minus 2, they're actually going to cancel out. 2 minus 2 is going to equal 0. So we're just going to have n over 2. And this is going to be 2n. Just to show you this once again, I hope this isn't too long. But if we have something like this, we can rearrange these terms, right? We could say 2 minus 2 plus 2n. And then we can see 2 minus 2 is equal to 0. And that is equal to just 2n. So when we're talking about addition, we can rearrange these values as long as we make sure to bring the negative along with it. And that's because addition is what's called associative. So yeah, two kind of properties of multiplication and addition. Commutative and associative properties. All right, last one. This step right here to simplify. N over 2 times 2n. In this case, let's rewrite this just slightly. So n over 2 times 2n, we can also write this as n over 2 times 2n over 1. And in this case, what do we have? On the top, we're going to multiply n times 2 times n. So n times n is going to be n squared, and then we'll have 2. So n times n is n squared, times 2 gives us 2n squared. And then this is all going to be over 2. And 2 over 2 is going to cancel out. And we're going to be left just with n squared. So that's actually the sum of n terms. If you want to know how many triangles there are for a cushion with n layers, you can actually just put in the value of the layers. So for example, let's say cushion with 2 layers, just put in 2 squared, and there's 1, 2, 3, 4 triangles. All right, so a lot of algebra kind of going on. I guess you would have to, on a time test, maybe ask the question, in terms of 2 marks, if you're comfortable with it, yeah, you can blast through. But in terms of method marks, substituting, this will already give you the first of the 2 method marks. And then of course, usually the kind of recommendation is 1 mark a minute. So if you're comfortable with this algebraic process, then you can work that out, very quickly, but always to maximize process and time management as well. All right, so there it is. Sum of n terms is equal to n squared. All right, part E. Write down the total number of black triangles in a cushion with 4 layers. So in this case, they give us the value of n. N is equal to 4. So in this case, S4 is equal to 4 squared. 4 squared is equal to 16. If you wanted to, you could also just count up to 4 layers and just simply count like we had here, for example. So 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is equal to 16. Maybe just to go back to this, if you wrote this out and weren't sure about the algebraic process, and you wanted to say, okay, how is the sum related to the number of layers? If we say, okay, well, let's see, S1 is equal to 1, S2 is equal to 4, that is to say the sum of all of these is equal to 4. S3, we're now adding on another 1, 2, 3, 4, 5 layers, so 4 plus 5 is 9. And S4, we're now adding on, 1, 2, 3, 4, 5, 6, 7, another 7 triangles. 9 plus 7 is equal to 16. You might say, hey, yeah, this is 1 squared, 2 squared, 3 squared, 4 squared, and then in all of these cases, it's just n squared. So potentially, you can show the substitution and then try to generalize by, I guess, just looking at this, what's called like inductively, seeing, hey, is there some kind of pattern here? And yeah, it's just n squared in this case. Okay, let's keep going. The number of black triangles in each layer forms an arithmetic sequence. Find and simplify an expression for the total number of black triangles in a cushion with n layers. So once again, we're looking at the total number, in this case, of black triangles with n layers. So let's actually look at this situation right here. So first off, let's see. Find and simplify an expression for the total number of black triangles in a cushion with n layers. Okay, so let's deal with just the number of black triangles. In term 1, or in layer 1, there's 1 black triangle. Here there's 2 black triangles, here there's 3 black triangles, and here there's 4 black triangles. So what could we say? So if we want to find the sum, once again, of n terms, what is that given by? It's given by n over 2, and we have 2u1 plus n minus 1 times d. So n, we don't know. That's what we're going to substitute. 2 times u1, the value, the number of black triangles in the first term is just 1. So this is 1 plus n minus 1. And in this case, the common difference is actually just 1. That's all we add to go from one term to the next. So d in this case is just 1. Oops. Let's clean this up. N over 2, 2 times 1, right here, 2 times 1 is just 2, plus, and in this case we just have 1 multiplied by n minus 1, so it's actually just n minus 1. Since we have an addition between the brackets don't really do anything. It's only when we're multiplying by in front of, let's say we have a coefficient, some plain number in front of a bracket, then that says we want to multiply everything within the brackets by that value. If we have an addition, the brackets actually don't actually serve any purpose, so we can remove the brackets. And now we can expand. N over 2, and then we have 2 minus 1 is 1, and we'll have just n plus 1 then. Okay, so there it is. That is our sum of black triangles with n layers. And if we wanted to, I suppose we could actually simplify this a little more. This is over 1. And now we have, I hope this isn't too much, n times n plus 1, n times n plus 1, then multiplying the bottom, 2 times 1 is just 2. Both of these are fine. This is our sum, and this is just a different way to express it. Okay. The total number of white triangles in a cushion with n layers is n multiplied by n minus 1 over 2. Part G asks, using both the given expression and your answer to part F, find and simplify an expression for the total number of black and white triangles in a cushion with n layers. Okay, this is kind of an interesting question. We actually already know an expression to find the total number of black and white triangles, because that's actually just the total number of triangles, and that's equal to n squared. So we kind of know the endpoint of what we should get when we add these two together. So once we add these two, that is to say, number of black plus number of white triangles, this should equal n squared. So let's go ahead and set this up. So Sn, total number of triangles, is going to be equal to black triangles plus white triangles, or white triangular prisms. In this case, black triangular prisms is given by n plus 1 over 2, and white triangular prisms is given by n minus 1 over 2. And now we're going to need to do some algebra, but we know the endpoint, I guess. Okay, so adding fractions, what do we have here? We have two fractions with the same common denominator. In this case, it would be something like, 1 over 7 plus 3 over 7 in this case, since they have a same common denominator, we can just go ahead and add the numerators. So let's go ahead and do that. Let's write this out over the common denominator of 2, because they're both the same, and we'll add the numerators. So we have n plus 1, plus n minus 1, all over this common denominator of 2. Now let's expand. N times n times 1. This is going to give us n squared plus n. Same here. N times n minus 1. N times n is n squared. N times negative 1 is a negative n. This is all over 2. Whoops. All over 2. All right. Let's group like terms. How many n squareds do we have? Well, here's 1. Here's 2. We have 2 n squareds. And how many n's? Well, we have this n, but then we also have a negative n, and they're actually going to cancel each other out. So they disappear. But we still have this 2 at the bottom. 2n squared over 2. 2's will cancel out. And we'll just have n squared, which is what we expected. Okay, so that ends this question. I want to actually look at the mark scheme to see what kind of process they're asking for, because it's an interesting question insofar as we actually know what the answer should be. So here's our mark scheme. So method mark 1 is showing number of black triangular prisms plus number of white triangular prisms. And then another method mark actually seems like they want to see it all over a common denominator with potentially expansion or bringing out this n over 2, factoring out n over 2, which is kind of interesting. And then in this final point, they're asking for the endpoint, this n squared. So, showing black triangles plus white triangles, some process, and then the final answer. Okay. Let's go on. Question 2. The diagram shows part of the graphs of the functions f of x is equal to 1.5 to the power of x, where x is greater than or equal to 0, and g of x is equal to 6 minus 3 over x, where x is greater than 0. So here's f of x equals 1.5 to the power of x, and g of x is equal to 6 minus 3 over x. Part A asked us to solve f of x is equal to g of x. So f of x is equal to g of x. This is f of x right here. Oops. This is f of x right here. This is g of x. We want to find the points where f of x is equal to g of x. In other words, we want to find the intersection points. What are the points on the graphs where f of x is equal to g of x? That would be point A and point B. So for this, we can actually just go ahead and graph both of these functions and then use the graphing calculator to find the point of intersections. So let's go ahead and do that. So here's our calculator. Let's go into our graphing section. 1.5 raised to the power of x. And then let's go menu, graph entry, and we will add 6 minus, and this is 3 over x. And now we have these two intersection points. So let's go ahead and menu, analyze graph, find the intersection point. Let's find the smaller intersection point first. So 0.6376, 1.295. Let's actually find the second intersection point as well. So lower bound, upper bound, and there it is. 4.0981 and 5.268. So let's go ahead and write this down in the document. So solve for f of x is equal to g of x. So essentially we actually don't need the coordinate point, we just need the x value. So looking at this once again, solve f of x is equal to g of x. What is the x value that will result in both of these having the same output? So for what x value will both of these have the same y value? For what x value, well, both of these have the same y value. So in this case, although we find the coordinate point, the point of intersection, we're really interested in the input. What is the input that we can feed into both of these functions that will result in the same output? And in this case, the first input for a would going to be when x is equal to 0.638, and also when x is equal to 4.098. So in this case, 4.098 turns into 4.10 to 3 sig figs. So I'm going to erase this and bring this over. Okay, so here are our values that solve for f of x is equal to g of x. I just want to check the mark scheme to see what would happen if you were to put in coordinates. So, so this is interesting. So it's a 3-mark question. They would give you A2, A0 if coordinate pair is given. So they are actually only asking for the x values here, because that's all we're really interested in terms of finding a solution. But if you were to have given the coordinate points, yes, you would find the x values kind of implicitly, but there'd be more information that's really needed, and maybe it shows not a complete understanding, I guess. So you would lose 1 mark. Okay. Okay, there we go. Part B, part 1 of B. Write down an integral that represents the area of the shaded region. Okay, so here's our shaded region right here. And we can ask, okay, it's the area under a given curve. The area under what curve? Well, the area under f of x. And in this case, for an integral, we need to write, are they asking, yeah, I guess we need to write what's called a definite integral. That is to say, we would need to provide the lower and upper bounds. So let's write an integral for this. I'm going to write it here actually. So this is bi. So an integral, I'm going to need a little more space actually. So an integral is, remember, essentially the sum of all the little rectangles. So the sum of what? Well, this function right here of f of x, which is 1.5 raised to the power of x. And then what is it? It's in terms of dx. Essentially that means the tiny, tiny little rectangles that we're going to sum. We're going to take the sum of the infinitely kind of small, in terms of the width, the small rectangles here. And what is the lower bound and what is the upper bound? Well, the lower bound is going to be 0.638. So find the sum of all those tiny, tiny, tiny little rectangles starting at 0.638, going all the way up to 410. All right, so once again, the integral is the sum. The sum of what? Well, all of these kind of vertically placed tiny little rectangles that we align up here. Starting at what point? Well, this lower bound, going up to this higher point, or this upper bound of 4.10. And what is the function itself? Well, 1.5 to the power of x. And dx just means in terms of these little tiny, 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 tiny little triangles here. All right, so that is the integral that represents the area of the shaded region. All right, part 2. Part 2 asks us to calculate the area of the shaded region. Okay, so we've already got the definite integral here. Now we just need to find essentially what it equals. So for this, we can go to our calculator and then find the result. All right, so here we are. Let's look at our functions right here. And here is our definite integral. So let's put our lower bound of 0.638 and our upper bound of 4.10. Our function itself was 1.5 raised to the power of x. and this is in terms of dx. So these should always match. Whatever your variable is here, just match it with the one here. And so far as I know, within AISL, I've only seen these in terms of x. All right, so here we have our area under the curve is 9.8078, or to 3 sig figs, 9.81. So let's go back to the document and write this out. So this would be 9.81, and this is B2, and I guess we could write this out as 9.81. If you wanted to as well, actually I've closed the graph, but you can also do this graphically as well. There's an integral function. Okay. Part 3. Hence or otherwise calculate the area of the region enclosed between curves y equals f of x and y equals g of x. Okay. So far what we found is this shaded area, but they're asking us to find the area enclosed between these two graphs. So essentially what they're asking us to find is this. All right, so how can we do that? We can actually find it directly, but I think in some ways that's actually going to be more challenging. And I think this hence also gives us a clue that we can make use of this area right here that we've already found. So I'm actually going to color code this just a little. Let me get a good color. Well, it doesn't matter so much, but here we go. So let's just call this the area that we found already, the shaded area. So what can we do? So if we were to look at this function g of x, which is 6 minus 3 over x, if we were to do that same process and find the area under the curve, we would find the area under this total, well, this curve, from this lower bound up to this higher bound. But that wouldn't just be this enclosed area, because it would also include this. So knowing what this red area is already, if we were to find the area under this curve from point A to point B, and then take away this area, then we would be just left with this enclosed area. So let's see if we can do that. So once again, we'll find an integral, in this case, for g of x. So let's find the area under the curve of g of x. So here we go. This is going to be integral, the sum of all the little triangles again, starting at that same lower bound of 638, going all the way up to 4.10. In this case, our function is 6 minus 3 over x, and then again in terms of dx. So let's find out what that is. So here we are in the calculator. Here's our definite integral. Once again, we have the same lower bounds and the same upper bound, but in this case our function is different. So this is 3 over x, and then again in terms of dx. All right, so it's larger, which is what we would expect, and it's 5.1908. I'm actually going to keep all of those digits and not round to 3 significant figures yet, because we're still within this question. We should only round to 3 sig figs once we've reached the end of the question. So let's go back to the document here. This is 15.1908. I actually want to erase this and just kind of provide another explanation of what's going on. So essentially what we did is we found with this 15.198, that refers to this entire set, this area under the curve right here. But we're not really interested in knowing this entire area. So what we found is, we can almost call it AT, the total area. So if we want to find just, let's say, A1, A2, the total area total, is equal to A1 plus A2. And that's what we found right now. We found this total area, the enclosed area plus the area underneath. That was this bound right here. But we don't want this bound. We want to take away A2 and just find A1. So in that case, what we're going to have is, well, the area under this curve minus the area under just this curve right here. So let's write that out. So we have 15.1908 minus 9.81. Let's go to the calculator and solve for that. So I'm just going to copy paste with all its decimals, I suppose. Minus 9.81. You don't need all of these decimals. Realistically, you only need maybe up to 3 or 4, I suppose. Okay, so this is the area that is enclosed between these two functions, 5.38. So let's go back to the calculator and write that out, or the document I mean. 5.38. Okay, so that would be the enclosed area right here of A1. Once again, area under the curve, we found this initially, we found A2. And using the same principles, we can find the area under this curve. But in that case, it also includes, well, the enclosed area and this area. It's the total area under the curve. We don't want the total though. We want to take away the shade area so that we could just find this enclosed area. So what do? Find the total area, take away the shaded, and then we find, well, what's left over, which is the enclosed area. All right, so hence or otherwise calculate the area of the region enclosed between the curves y equals f of x and y equals g of x. Okay, that's what we've done, and it's 5.38. Okay. Okay, final question here. The tangent to the graph of y equals f of x is parallel to the tangent to the graph of y equals g of x at x is equal to k. Find the value of k. So essentially what they're asking in rather plain terms is, what point is there on the graph? At what point do both of these graphs have the same slope? Slope being the instantaneous rate of change at any of these given points. So essentially we have two tangent lines. What is a tangent line? A tangent line is a line that just glances, that just touches a function at one and only one point and tells us the instantaneous rate of change. So here is, for example, a tangent line. We can do the same thing here, and we can draw a tangent line once again. So it tells us the slope at this given point, and it just touches, in theory, it just glances this function at one and only one point. And if we have two tangent lines, one on this function and one on this function, and they are parallel to one another, that means they have the same slope. So it's unclear where exactly that might be, but just kind of making a kind of estimate. Let's say, it's maybe a little difficult, but potentially right around here or so. We might say, hey, this looks reasonable enough, and I'm actually going to copy this just so it is actually parallel. And then we might say, at least in theory, it should be also right here at this given point. At this given point right here. That is to say, for the same x value, they have the same slope. So what is the point on f of x and g of x where they have the same slope? That is to say, where the tangent lines themselves are parallel. And that's the question. That's actually a difficult question, I think. So let's go ahead and try to unpack this a little. What do we have? We have f of x and g of x. F of x is a function, takes inputs, and then it gives us a corresponding y value and output. But what about the derivative, f prime of x? Because we're talking about, let's say, tangent lines and the slopes of lines. So when those two kind of ideas come to us, okay, a slope of a line, slope is an instantaneous rate of change. What kind of function comes to mind? Well, our derivative. So in this case, our normal function, put in some value of x, it spits out some value of y. Our derivative function, or our gradient function really, we put in some value of x, and out comes the instantaneous rate of change, or the slope. So if we have some derivative, we feed in some value of x, it'll give us the slope. And essentially, what we can do with that is say, okay, well, if this input into x, if we feed, let's say, some value of x into our derivative function, it will give us the slope. similarly, if we feed some x value into g prime of x, or the derivative of g of x, then it will also give us a slope. If we want to find the situation where we have the same slope for g of x and h of x, essentially what we're asking is, where is the point where f prime of x is equal to g prime of x? That is to say, the point where, with the same x value, they have the same slope. So once again, this is our derivative function. It will tell us the slope, or the instantaneous rate of change, the gradient at any given point of x. And we want to find where is that point where the slope of f of x is equal to the slope of g of x. So essentially, this is what we want to solve. F prime of x is equal to g prime of x. So let's go ahead. And what makes this an extra challenging question is that within AISL, we don't exactly have the tools to take the derivative of this and work this out algebraically. So we're going to use our calculator, we're going to need to n solve, and we're going to kind of need to do this in a way that isn't so common, isn't often, I guess, directly taught in some kind of ways, actually. So here we are, let's go to the calculator. We're going to need to set up an equation, so we're going to need to n solve. And we want to say the derivative of f of x. So let's go into our function. This, remember, is our integral. And remember, for f prime of x, actually maybe I'll go back to the document for a sec. So here we are, f prime of x. We can also write this as dy dx, right? So going back to the calculator once again, here is our derivative, d dx. So d over dx, d dx of our function, f of x, which is 1.5 raised to the power of x. This should be equal to the derivative of g of x as well. So let's set up a derivative once again. And we'll set that up for g of x, which was given by 6 minus 3 over x. And just like we do with n solve, we ask it to solve for x. So although this looks maybe a little challenging, this is the derivative function. So when does the derivative of 1.5 raised to the power of x equal the derivative of 6 minus 3 of x? In plain language, what is the point on each of these functions where they will have the same slope? For what value of x will they equal to one another? For what value of x will they have the same slope? And that's at 1.864. All right, so let's go back to the document and write that out. Okay, so x in this case is equal to 1.864, or to 3 sig figs 1.86. All right. Question 3. According to the timetable, the evening train from Cardiff arrives in London at 6 p.m. Records show that the arrival times for this train are normally distributed with a mean arrival time of 6:20 p.m. and a standard deviation of 10 minutes. Let x be the random variable, the number of minutes late the train arrives. Part A asks us to write down, and then section 1 is the mean of x. So we need to write down the mean of x. So key word that kind of sticks out is normally distributed. So we're in the realm of normal distributions, and that's going to help, I think, scaffold and kind of narrow down the process in some ways. Or it tells us what to focus on in some sense. So write down the mean of x. X refers to the number of minutes late the train arrives. The train is supposed to arrive at 6 p.m., but on average, its mean arrival is 6:20. So the mean number of minutes late is 20. On average, it arrives 20 minutes late. Part 2 asks us for the variance of x. So variance is another measure of spread, how spread out the data is. So variance, this isn't actually given to us in the formula booklet. Variance is equal to standard deviation squared. We know the standard deviation. The standard deviation is given to us as 10. So the variance is 10 squared, or 100. All right. So that's the first two parts of this question. I guess I can leave this here. All right, so let's go on to part B. Part B says, or asks us to find the probability that the evening train arrives in London between 15 and 25 minutes late. So for this, I'm actually just going to draw a normal distribution. You can actually, for a lot of these questions, sketching out a normal distribution with the area shaded, the correct area shaded, is a method mark. So let's actually just draw a normal distribution to kind of show what's going on here. So here's a normal distribution. Normal distribution is symmetrical, centered about the mean. We can call the mean mu. And mu in this case is the mean, and it refers to the number of minutes late. So on average, a train is 20 minutes late. So in the earlier part, I don't know if we kind of skipped this or went too quickly in some ways, but just to sketch this out a little further, this is the original time. This is the time at which the train is supposed to arrive, and this is the average time at which it arrives. So if x itself is the number of minutes late the train arrives, the mean number of minutes late is 20, and that's why we wrote 20 up here. So getting back to part B, they ask us to find the probability that the evening train arrives in London between 15 and 25 minutes late. So if it arrives at 6, it's on time. Anything after this, it's late. So what are the bounds? What is that shaded area? Remember, our standard normal curve represents all possible situations. The area under the curve is equal to 1. So essentially we're asking what fraction of this total set is between 15 and 25 minutes. So here's our mean of 20. Let's draw the upper and lower bounds. Let's use blue, I suppose, or green, I guess. So here we have 15 minutes late. 15 minutes. Is this showing up? There we go. 15 minutes late. Let's do this. This is okay. So this is 15 minutes. And this right here would be 25 minutes. And essentially the question we're asking is, what fraction of this normal distribution is within these bounds, within the bounds of 15 and 25? So what are we asking? We're asking essentially the question, probability that a train arrives, this is mean minutes late for x, between 15 and 25 minutes late. And for this, we can go to the calculator and we'll look at normal distribution for this. So let's go menu, probability, distributions, and we want to go to normal CDF. So in this case, our lower bound is 15, upper bound is 25. Our mean in this case was 20, and our standard deviation was 10. And they gave us this in the question. So once again, between 15 and 25 minutes, our mean minutes late is 20, standard deviation is 10. All right, so 0.3829 or 0.383 as a percent, that would be 38.3 or 38.3% of the time. The train is between 15 and 25 minutes late. So let's write that out. Going back to the document here, we have an answer, which I'm going to write it here, of 0.383. Or if we wanted to, we could represent this as 38.3%. If this is a little unfamiliar, the mark scheme it says specifically that it says condone calculator notation. So if you're wondering how can I get this process mark, if this seems a little unfamiliar, you can actually write down calculator notation. So for example, if your process or your method marks were just writing off of the calculator screen of norm CDF and then showing lower bound, upper bound, essentially what's written on the calculator, mean, standard deviation, you could just write that as well. And this would be a perfectly acceptable method as well. All right. Let's go on. If the train arrives more than 30 minutes late, the train company must pay a fine. calculate the expected number of days in a 365-day year that the train company pays a fine. Okay, that's interesting. So first off, to find the expected frequency, or the expected number of days out of a total year of 365 days that the train company would need to pay a fine, we first need to find out the likelihood that a train is going to arrive 30 minutes late. So let's go back to this normal distribution. I'm going to try to clean it up a little and see if we can work with this actually. So we can use the same normal distribution. To be honest, I don't think I'm going to get rid of all of this. Actually, I think that's okay. Not bad. Okay, so in this case, we have different bounds. We want to find the probability that the train arrives more than 30 minutes late. So let's draw that bound in this case. So let's call this is maybe 30 minutes. 30 minutes right here. And essentially we want to find this area, everything to the right here. What is the percentage? So what is the probability that this train arrives more than 30 minutes late? This is again going to be a normal distribution question. So let's go back to the calculator and find out the probability. Actually, before that, let's write out what that would look like. This is the probability that mean number of minutes late is greater than 30 minutes. Okay. So let's go to the calculator here. Menu, probability, distributions, normal CDF. In this case, our lower bound is 30. Our upper bound, we can put in anything as long as we are guaranteed more or less to capture all the area to the right. In practice, 100 would be okay, but if you want, you can just write 99999. This is essentially 9,999 minutes, and so. Mean is again 20, standard deviation is 10. Okay, so what do we have here? 0.158655 or 0.159. As a percentage, 15.9% of the time, this train is arriving 30 minutes or more late, or it's arriving more than 30 minutes late. So let's go back to the document. I'm going to actually write this, running out of space here, not too much. And actually I'll just write this here. So the probability that this train arrives 30 minutes late or more is equal to 0.159. And once again, if you want to write calculator notation, that is perfectly acceptable. You could write norm CDF, lower bound, upper bound, mean, standard deviation, and then once again, this is 0.159. As a percent, 15.9%. But we're not done yet. 15.9% of the time, this train is arriving late. So out of 365 days in a year, well, what fraction of the year, or what fraction of this total amount of time could we expect the train to arrive late? Well, 15.9% of this total set. So it doesn't arrive all the time, doesn't arrive late all the time, doesn't arrive late half of the time. In that case, we would just take half of this value. Only 15.9% out of the year, this train arrives late. So in terms of our expected frequency, we can actually just use this. Ex is equal to n times p. So in this case, we have 365 times 0.159. So essentially 15.9% of 365. Let's go to the calculator and work this out. 365 times 0. Actually, better accuracy. Let's just copy paste this. That's a fair bit of accuracy. That's good, I suppose. 57.9092. Okay, so that's our answer. 57.9 would be the number of times that we could expect this train to arrive late. In this case, we could actually leave this as a decimal. So going back to the document here, we can write this as 57.9. And you might be wondering, okay, isn't this Shouldn't we have a whole number value? That is to say, a train can't arrive, 0.9% late. I mean, it can arrive 0.9% late, but in terms of the number of days that it arrives late, we can't say, this 0.9 here. It would either need to arrive late on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 days. So you might be inclined to write 58, and the mark scheme actually accepts both. You could write 57.9 or 58 here. For expected value, however, you can always write this decimal. So 57.9 is fine. Okay, let's go on. Janine arrives in London on the evening train from Cardiff. She then has to catch a connecting train. She allows 10 minutes to change platforms at the station. She requires the minimum probability of arriving at the platform to catch the connecting train to be 99%. Part D asks us to find the earliest time, correct to the nearest minute, that the connecting train would depart to meet Janine's requirements. Okay, so this is kind of an interesting question. It's a 4-mark question, and to be honest, I think the wording is actually a little confusing. I think it could potentially be stated in more straightforward terms. Essentially what they're asking here in this case is Janine wants to catch a train. She's going to be coming in from Cardiff. She's going to be arriving into London. She wants to, you can imagine, book this train in advance. She knows that this train arrives late, and it doesn't arrive on time, it arrives according to this distribution. She wants to make sure that she doesn't miss her train. So in terms of booking it early, how can she be 99% sure that she catches it? So what is the earliest time? What is the earliest time she should book her next train out of London, knowing that this train from Cardiff arrives, within these bounds, along this kind of normal distribution? She wants to be sure that she catches this train, this connecting train, 99% of the time. So when should she book it? So let's actually go and let's draw another normal distribution here. Okay, so once again, we have this normal distribution, a mean of 20, and she wants to be 99% sure that she is going to catch this train. In this case, we have the percentage and we want to find the time. In these earlier questions, we had the time. That is to say, we had these lower and upper bounds. We had this upper bound of 30 minutes. We had the time and we wanted to find the percentage. Here, we have the percentage and we want to find the corresponding time. So essentially what we have is inverse normal. We know that 99% of the time, so she wants to have 99% of the cases covered. What is that time that will make that true? So essentially, train arrives, what can we say? The train arrives on time at 6 o'clock, maybe it even arrives early. All the way up here, all the way up to some point right here, where we can say that 99% of the values are to the left of this point. So 99% of the values are to the left. What is this value, this time right here, in which 99% of the values are to the left? So essentially, we have a percent. Now we need to find the time. We're in the realm of inverse normal. So let's go ahead and go to the calculator for this. Menu, probability, distributions. In this case, we want to go inverse normal. The area, so remember, calculator sweeps out from the left to the right. In this case, we want 99, so 0.99. Mean, once again, is 20. Standard deviation is 10. So with this normal distribution, not here, guess we'll have to do it again. Probability, distributions, inverse normal. Okay, hopefully it shows up here. There we are. So if the train arrives, so 99% of the time, the train will arrive within 43 minutes, 43.26 minutes of its scheduled arrival. So train is expected to arrive at 6 o'clock. 99% of the time, the train will arrive within 43.26 minutes of this arrival time. So if she wants to be absolutely 99% sure, not absolutely, but if she wants to be 99% sure, she's going to need to plan for this train to arrive up to 43.26 minutes late. So let's go back to the document and fill in some of this. All right. So this value corresponds to 43.264. But remember, she also wanted to, I think there was a 10-minute, she wanted to allow this kind of grace period or this 10 minutes to change platforms. So she can't just book a train at 6:43, for example, because she wants to have 10 minutes to change platforms. So in this case, what we're going to need to do to find this total answer is have 43.264 plus 10 minutes. So this is 10 minutes to change platforms. And overall, this will be 53.264, or to 3 sig figs, 53.3 minutes. We don't usually write minutes with this decimal, we usually write it in seconds, but I don't think they're asking 4 minutes in seconds. So in this case, probably just save some time and let's write it as 53.3 minutes. So the earliest time correct to the nearest minute, that would be 53 minutes then. The nearest time correct to the nearest minute that the connecting train could depart to meet Janine's requirements would be 53 minutes. Once again, 99% of the time, the train will arrive up to 43.264 minutes late. Anything beyond this becomes increasingly likely. Not to say it's not impossible, but for her level of certainty, she just wants to be 99% sure. So if she books her next train 43.264 minutes after this, and then providing herself 10 minutes to change platforms, the earliest time she would want to book is, 53 minutes after this. The earliest time is, 6:53 then. Okay, so I hope that's clear. 6:53, why would it be 6:53? Because this is its scheduled arrival. This is 43 minutes late, and then this is plus another 10 minutes. So relative to this scheduled arrival of 6, she needs to book it at 6:53. All right. Okay. I think maybe I'll say this now, I suppose. But I think this is an interesting question because it's not necessarily like offensive to like the London or like the English train system, but this is the first time I've seen this in an exam where all the way at the end they have this disclaimer where it says content used in IB assessments is taken from authentic third-party sources. The views expressed within them belong to their individual authors and or publishers and do not necessarily reflect the views of the IB, which is kind of interesting. So if this is offensive to, let's say, the English train system, well, it's not necessarily the view of the IB. Potentially. Not necessarily. Okay, let's go on. Maybe just a kind of interesting little fact, I suppose. Okay, let's go on. David, an employee of the train company, is concerned about the number of trains being late. He spends 7 days in London noting the arrivals of trains. It can be assumed that train arrivals are independent, so one being late doesn't influence the chance of the other being late. Part E asks us to find the probability that the Cardiff to London evening train arrives late on the first day that David is in London. So, going all the way back to the top, it's supposed to arrive at 6. On average, it arrives 20 minutes late, We just want to find the probability that it arrives late, even a fraction of a second late. So find the probability that the Cardiff to London evening train arrives late on the first day. So what is the probability that this train arrives late, even a fraction of a second? Let's erase this. And I think we can use this normal distribution again. So let's go ahead and do that. Okay. So here we have our normal distribution, once again, centered at the mean. The train is supposed to arrive at 6, right here. So essentially we want to ask, what is the probability that mean number of minutes late is greater than 0? And this is essentially going back to our normal distribution once again. So let's go to the calculator here. Probability, distributions, normal CDF. Lower bound is 0. Upper bound, we just want to find out, make sure that we clear all information to the right. Mean is 20, standard deviation is 10. Okay, so the probability that this train arrives late is 0.977, or 97.7% of the time. So let's go back to the document here, write that out. 0.977. Once again, you can use calculator notation for your process. Norm CDF, and then we can say lower bound, upper bound, mean, standard deviation, and then the answer once again. Okay, let's go on to part 2. So we want to find the probability that the Cardiff to London evening train arrives late on 5 of the 7 days that David is in London. Okay, so oftentimes the AISL papers will bunch, or not bunch, but you will see these two concepts, especially on a paper 2 side by side. That is to say, probability concepts of normal distribution, inverse normal, and then binomial. So how do we know that this is binomial? We have a set number of trials, 7 days. The trials themselves are independent. They don't influence each other. And then we have a finite number of what we call successes. In this case, I guess the event that we are interested in finding out about. In this case, the chances of it being late. So we're in the realm of binomial distributions. We want to find out the probability that the evening train arrives late out of 5 out of the 7 days. So this is going to be binomial CDF. This is a binomial CDF question. I'm going to move this, if I can, up here, and then we'll work this out on the calculator and find this binomial. Okay, so here's question E1, and now let's go to E2. So we've got a binomial. Let's go to the calculator. Menu, probability, distributions, and in this case we want to go to binomial CDF. Number of trials, in this case the individual David is there for 7 days. Probability of success. We're defining success as the event that we're interested in finding out. It's not necessarily a good thing or a bad thing. It is just what we're interested in finding out, the outcome that we're interested in. And in this case, it's the chance of a train being late. So success we're defining as late. We want to know what is the probability that there are 5 successes. All right, oops, sorry, this is probability of success. Probability of success we found to be 97%, so 0.977. So it still works, the idea that success isn't necessarily good or bad, it's just what we're interested in measuring. Number of trials is 7. Probability that the train is late is 0.977. In this case, we want a lower bound of 5, and in this case we can say upper bound of 5 as well, because it's not 5 or more, it's on 5 of the 7 days, in whatever kind of order. So lower bound and upper bound is 5. We could have actually used PDF for this, but I think it's always, not always necessarily, but I think using CDF for both normal and binomial is potentially less confusing because there's no such thing as normal PDF in AISL that we use. So always keeping it to CDF means that you'll never necessarily get confused with lower bound, upper bound questions when you're dealing with normal distributions. So here we are, once again, 7 trials, probability of success. We want to know 5 out of 7 times this probability, or the chance of this train being late 5 out of 7 times. Here we go. So the chance of this train being late 5 out of 7 times is 0.009889. So almost just a 1/10%. So let's go back to the document and write this out. We can write this as binom. If you chose PDF, that's perfectly fine as well. And maybe even actually a little better in terms of form, but they're both okay. 0.97755, and then the probability of this is 0.009889, or to 3 sig figs 989. Okay, let's keep going. Part 3 of question E. Find the probability that the Cardiff to London evening train arrives late on at least 5 consecutive days that David is in London. So there's one word here that changes the nature of this question, and that's the word consecutive, because it tells us that order matters. In comparison to question 2, where we wanted to find the probability that the train arrives late on 5 of the 7 days, here order didn't matter. The train could have arrived late, for example, on the first 5 days, and then on time for the last 2. That would have satisfied this situation. Or it could have arrived late and then on time, and then late for 4 days in a row, and then on time, and that again would have satisfied the idea that the train is late on 5 of the 7 days. Here, however, we want to find the probability that the train is late on at least 5 consecutive days that David is in London. So here order matters because we want to see the probability that it's late on consecutive days, 5 or more. So 5 days in a row, 6 days, or 7 days in a row. So this changes the nature of the question. We can no longer use binomial distribution, but we're going to have to look at the set of possible outcomes that in some ways conform or that satisfy the situation of this train being late on consecutive days. So let's draw a diagram here and try to represent what's going on. So David is in London for 7 days. So here it's 1, 2, 3, 4, 5, 6, 7. And let's look at one situation where, let's say we can have 5 consecutive days where the train is late. That would be late, 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 and then on time, on time. That's one situation where we can see 5 consecutive days. But there are others. For example, 2, 3, 4, 5, 6, 7. I'm actually going to copy this just to save time, because we're going to need a few more actually later. The other situation where we can see 5 consecutive days is it can be on time, and then it can be late for 5 days, and then on time once again. This satisfies the idea that the train is late on 5 consecutive days. We can also have the situation where the train is on time for the first 2 days, and then it's late on the last 5 days. This would also be a situation where we see the train late on 5 consecutive days. But we're not quite done yet because it's on at least 5 consecutive days. So potentially the train could be late 6 consecutive days. So 6 days in a row. Let me see if we can do that. There we go. So what does that look like? Well, the train could be late on the first 6 days, and then it could be on time for the last. Or similarly, it could be on time and then late for the last 6 days. The other situation, and the final situation, if we want to find out at least 5 days or more. So in this case, The train being late every single day would also match the situation where David witnesses the train being late on 5 or more consecutive days. All right, so these are all of the possible events that conform or that satisfy the situation that the train is late on 5 consecutive days or more. So we could have actually drawn, in some ways, like the most complex kind of tree diagram, and it could have worked, but I guess I say that because we're going to use a similar process. In the same way that we sum the possible situations, or the branches that conform to the set of outcomes that we're interested in, we're going to do the same thing here. We're going to find the probability of this event, probability of this event, and so on, and then we're going to add up all of those probabilities. So it's going to be a little bit of calculation, but we can condense that and make it a little more efficient in some ways. So let's first look at the probability of this situation. That is to say 5 lates and then 2 on time. So what is the probability that the train is late? I guess first off, remember these are independent events, so they don't influence each other. That means, just like in tree diagrams as well, we can multiply along the branches. Here we can multiply by lates, on time, and it doesn't, well, that's what we could do for independent events. We can multiply along the branches. This, I guess, relates to this idea of PA times B for probability of independent events is just A times B. And we can extend that to, well, in this case, 7 events. Okay, so what's the probability that a train is late? 0.977. So 0.977 times 0.977. This is going to be a little bit much, but that's fine, I suppose. Times 0.977. And these are binary situations. So binary means either or. One of these things has to happen. So in this case, the complement of late is on time. It's either late or on time. So what is left over? What is the complement of late? It's 1 minus 0.977, or in this case, 0.23. And this would be the probability of not late, right? Which is the same thing as probability of on time. So probability of on time is 0.23 times 0.23. Okay, so that was quite an ordeal. And that would be this situation right here. Now, if we wanted to condense this, how could we write it? I'm going to actually move this over just slightly. How could we write this if we wanted to condense this information? Well, we have 0.977 multiplied by itself 5 times. So all of this itself would equal 0.977 multiplied by itself 5 times, that's saying raised to the power of 5 with the exponent of 5, times 0.23 multiplied by itself twice. So this would be times 0.23, 23 multiplied by itself, well, twice, or squared. All right, let's go and look at the next possible situation here. So this is the probability that we have the train arriving late 5 times and then on time for the last 2. Let's find the probability that this train is on time, late, and on time. And then after this, we'll be able to condense this and go a little quicker. So on time, 0.23 times 0.977 times 0.977 times 0.977. And then by now we can say, okay, well, how many times are we multiplying, let's say, on time and late by themselves in each of these situations? Well, here, once again, we're going to multiply on time by itself, well, twice, and we're going to multiply late by itself, which is 0.977, by itself 5 times. So we're going to have 0.23 times 0.23, or 0.23 squared. And we're going to have 0.977 times 0.977 times 0.977 multiplied by itself 5 times, so raised to the exponent of 5. So in the end, we'll have the exact same situation 0.977 raised to the power of 5 and 0.23 squared. So why do they look the exact same? Because when we multiply, for example, a times b times c, that's the exact same thing as c times b times a or b times c times a. Order doesn't matter when we multiply. And in these situations, all we really need to know is that we're multiplying 0.977 by itself 5 times, 0.23 by itself 2 times. And that's exactly what we have here, although the order is different. And in this case as well, we're going to multiply 0.977 by itself 5 times and 0.23 by itself 2 times. So we can start to condense this and speed things up a little. So 0.977 raised to the power of 5. This is 0.23 squared. Okay, let's look at this situation. We have 0.97, that's the probability of it being late. We're going to multiply it by itself 6 times. So here we have 0.977 raised to the power of 6, and we're going to multiply by 0.23 once. This is going to be the exact same situation as well, multiplying by 0.977 6 times, and then multiplying by 0.23 once. 977 6 times, and 0.23 once. In this last situation, we're just going to multiply by 0.977. Well, 7 times we're going to multiply it by itself. Okay, so these are all of the possible situations or all of the possible outcomes where the train arrives late consecutively on 5 or more days. So just like in a tree diagram where we sum all of the possible events that conform to the given outcome that we're interested in, we can do the exact same thing here. So let's start writing this out. Okay, again, we can condense this through a little bit of algebra. So really we could do 0.977 raised to the power of 5 times 0.23 squared plus this, plus this, plus this, plus this, plus this. We could do that, and that would get you the correct answer. But we can also bunch things and condense things just a little. So what do we have? We have 0.977 raised to the power of 5 times 0.23 squared. And how many times does this occur? Well, plus, it occurs 3 times, right? So in this case, we want 3 of these. So we could say 3 times 0.977 raised to the power of 5 times 0.23 squared. So 3 times this. Plus, again, we have this situation right here. And how often does that occur? Well, that occurs twice. We have 2 of those. So we could say, this plus this, but we have 2 of the exact same thing. So let's just take this, multiply it by 2, and then we've captured all of it. So plus 2 times 0.977 raised to the power of 6 times 0.23, just multiplied by itself. And then lastly, we have this situation here, which only happens once. And that is 0.977 raised to the power of 7. Okay, so here it is. These are all of the possible events that satisfy the situation where the train is arriving late 5 or more times. Now we can go to our calculator and work this out, and that is the last step. So let's go and open up a calculator screen. 3 times 0.977 raised to the power of 5 times 0.23 squared plus 2 times 0.977 raised to the power of 6 times 0.23 plus 0.977 raised to the power of 7. I think that is good. I just want to check because we've done a lot of work so far. Make sure everything is correct. And that is not good because that is a probability greater than 1. So let's actually check this. I think something went wrong. Okay. Let's look at this right from the beginning. 3 times 0.977, here we go. So it's not 0.23, it's 0.023. So I'm going to actually copy paste this. Actually, it's already copy pasted. It shouldn't be 0.23, it's 0.023. So, of course, if you get a value greater than 1, probability can't be greater than 1. That would be certain is already 100%. So 977 complement 0.023. Good. Now, here we go. 0.89112, or 0.891. That is the probability that David sees the train coming in late 5 consecutive days, or 6 consecutive days, or 7 consecutive days. 5 or more consecutive days. So let's go back to the document here, and we'll write that out. And that was quite a challenging question. 0.89112, or 0.891 to 3 significant figures. Okay. All right, so I think that's good. Question 4. The circular clock face of a grandfather clock is 30 centimeters in diameter and its lowest point is 120 centimeters above the ground. The length of the minute hand is 15 centimeters and the length of the hour hand is 10 centimeters. This is shown in the diagram. The clock is started at 3 p.m. precisely. And so here we have this grandfather clock. It's 120 centimeters off the ground. That's the start of this, I guess, dial. And then here we have the hands themselves, 15 centimeters for the minute hand and 10 centimeters for the hour hand. Write down the size of the angle between the hour hand and the minute hand of the clock at 3 p.m. So here's 3 p.m. What is the angle between the hour hand and the minute hand? Well, 3 p.m. is at a right angle. This is a right angle. So this, of course, would be 90 degrees. Part 2 of Part A. Calculate the distance between the tips of the 2 hands of the clock at 3 p.m. Okay, so here's the tip of the minute hand, here's the tip of the hour hand. We know we have a right angle right here, so often in an IB question they ask us to make use of the previous information. So, extending both tips, we see that we can form a right angle triangle, and in this case with the right angle triangle, we can go ahead and use Pythagorean theorem. So once again, I'll just draw a quick right angle triangle right here. Something like that. We have one side length of 10 centimeters, the other of 15, and we'll want to find D. What is the Pythagorean theorem? It's a squared plus b squared equals c squared, or the sum of the squares of the smaller side lengths or legs of this triangle is equal to the square of the hypotenuse. So what is this? This is 10 squared plus 15 squared is equal to, and here we actually called it d, so maybe we'll call both of these d, is equal to d squared. We don't want d squared exactly, we just want d, so let's take the square root of both sides. And now we have 10 squared plus 15 squared, and that should be our answer. So let's go to the calculator and work this out. So let's open up a square root. And the question is, what is 10 squared plus 15 squared? All right, and the answer is 18.027 or 18.03 or just 18.023 sig figs. All right, let's go back to the document. 18.03 is equal to D. Therefore, D is equal to just 18.0, and then our units are centimeters. Okay. Let's move on. Moving on here, it looks like we've got a trigonometric function. The height of the tip of the minute hand, f of t, above the ground can be modeled by the cosine function. F of t is equal to a cos bt plus d, where a and b are both greater than 0. Okay. Where the angle bt is measured in degrees and t is the number of minutes after 3 p.m. So t is our input, it's what we substitute into this function, and it is the number of minutes after 3 p.m. So 3 p.m. is essentially our starting point. Okay, so f of t represents the height of the minute hand above the ground. And we want to try to create a function that allows us to determine the height of the minute hand above the ground at any given point in time. Okay. A sketch of the graph of y equals f of t as time passes from 3 p.m. to 4 p.m. is shown. Okay, so they tell us 3 p.m. to 4 p.m. because this is the time it takes for one complete cycle. That is to say, the time for this minute hand to sweep through one revolution. All right, part B. Write down the value of m, and then part 2 of this is write down the value of n. So let's go ahead and look at what these values are. So right here, m and n. M is the highest point that this minute hand reaches above the ground, and n, again being the output of this function, would be the lowest point above the ground. So let's actually go to our diagram, and I think this might be the best visual representation. So if this function represents the height of the minute hand above the ground, the dial itself starts at 120. The highest point it's ever going to be is going to be, well, 120 plus 30, or 150. And of course, the lowest point it's ever going to be is just going to be 120 right there. So once again, this minute hand sweeps through revolutions. What is the highest point? Well, when it strikes 12, that's when we have 120 plus 30. And its lowest point is just going to be 120 centimeters, 120 centimeters off the ground. All right. So what is m? M is the highest point, and it is, once again, 120 plus 30, or 150 centimeters off the ground. N is the lowest point, and it is only equal to 120 centimeters. Okay, let's keep going. Moving on to part C. Hence, find the value of, we have A, B, and D. And this word hence is actually key because it tells us in some ways to make use of what has come before. So in this case, this max and min. So A, B, and D, what do these refer to? These are variables within our cosine function. So cosine, remember, starts at the very top and then sweeps through and then goes back to the top. And each of these, we can say, transform our function in some kind of way. They either stretch it out, they shift it up or down, or they squish it together horizontally or stretch it out horizontally. And it allows us to map a basic cosine function to some situation in the real world, like this clock, for example, this minute hand. So let's go ahead and start with A. This is only a 3-mark question. And what makes, I think, these questions maybe most challenging is because the formulas are not exactly given to us within the formula booklet. So what is A? What is this coefficient here referred to? It is the amplitude of our function. So in this case, what is amplitude? Amplitude is the distance from the midline of our function, sine or cosine function, to its highest or lowest point. So in this case, amplitude would be, for example, oops, that's a little funny. Amplitude would be this line here, or sorry, this distance from the midline to the max, or for example, the distance from the midline to the minimum. Essentially the height of the wave, that's what our amplitude is. A few different ways that we can solve this. I think the most straightforward way is actually to use this formula. The amplitude is itself maximum minus minimum divided by 2. And this naturally extends from this idea that the amplitude is essentially the height of our wave, or the distance from the midline to the maximum. That is to say, if we know the total distance, in this case maybe I'll get a different color. If we know the distance from the top to the bottom, this would essentially be 2a. So if this is the distance from the top to the bottom, and we really actually want to know the distance from the halfway point to the top, then we can take the max minus min, which is essentially going to be this total distance, and divide by 2, and that will give us the height of the wave itself. So let's go and write that out. Max we saw was 150. Oops. And the min was 120. Over 2. 150 over 120 is 30 over 2, and that's equal to 15. So A itself is equal to 15. All right, let's write that out. A is equal to 15. Okay. All right, so the height of the wave, the amplitude, is equal to 15. Okay, section B, or part B right here. B is, I think, the most challenging to find. It is the frequency. It tells us how many revolutions there are within 360 units, which is maybe a kind of strange way to phrase it, because why 360? Well, it has something to do with the unit circle and the fact that we return to our starting position after traveling through, for example, 360 degrees. The unit circle actually starts here and then goes around like this, but that's what our frequency is. The frequency tells us the number of revolutions that occur within 360 units. And the units are, in some ways, agnostic and kind of neutral. They can be, in this case, minutes, or they can be hours, they can be seconds, they can be vibrations, but 360 units. How many revolutions occur within 360 units? That is, I suppose, our kind of theoretical underpinning in some ways. But what is the formula that allows us to calculate B? Well, B is equal to 360 divided by the period. This is, okay, well, what is the period? The period is the time taken to pass through one revolution, or in practical terms, the time taken to go from one point back to that point. In this case, we have, let me get a new color. I guess I'll use blue again. We have the time taken to go from one peak to another peak, or another way we could do trough to trough and so on, but the time taken is, well, 60 minutes. So the time taken to sweep through one revolution is, well, 1 minute for our minute hand. 60 minutes for our minute hand. So B is equal to 360 over the period. Period is equal to 60, and therefore 360 divided by 6 is just equal to 6. All right. Once again, our formula for B, the frequency, is 360 divided by period, where period is the time taken to sweep through one revolution. In this case, it takes 60 minutes to sweep through one revolution. 360 over 60 is equal to 6. All right, so B is equal to 6. And D is actually one of the easier ones to find. D is essentially the location of the midline. So normally, our cosine function, for example, let me just draw a quick cosine function. Normally our cosine function is, if this is, let's say, x and y, and this is, of course, 0, 0, right here. What does our cosine look like? It starts at the top at 1, goes all the way down to -1, but it goes like this, and so on and so on. But it's centered about this line y is equal to 0. But not all of our trigonometric functions are going to be like this. We sometimes want to shift them up or down. And so in this case, this value of d is the value that we shift our cosine or sine function up or down by. Essentially, it's the location of the midline. Usually the midline is 0, just by default. In this case, in this function, what is the location of the midline? And that's what d is. So we have another formula for this, but we can also use intuition. The value of d, or the midline, let's maybe just write it as d here, is equal to max plus min over 2. Essentially the halfway point between the max and the min, that's going to be our midline right here. So max plus min, 150 plus 120 over 2. What is the halfway point between these two? I believe that would be 135. Okay. So d is equal to 135. All right, and with that, we have transformed our basic cosine function into this function that maps the height of the minute hand through time. And that's essentially what we do for a lot of our modeling functions when we deal with trig. Okay. Question 4. Continued. The height of the tip of the hour hand, g of t, above the ground can be modeled by the sine function. G of t is equal to p sine qt plus d, where qt is measured in degrees and t is the number of minutes after 3 p.m. Show that q is equal to 0.5. Okay, so q once again is our frequency. So we shouldn't get confused. Oftentimes we'll see this. We'll see f of x, or you could even see y, for example, is equal to, and then for sine or cos, it would be something like a sine b of x plus d. But we shouldn't get confused if, for example, a is now written as p, or b, the value that we multiply the x or our input by, is now q, and our input is no longer some generic x, but it's t for time. We can use different letters to refer to essentially the same feature or characteristic within our function. So this number in front, this coefficient in front of sine, that's the same as a. It's the same amplitude that we saw the first time around. This b is still the same frequency, the number of revolutions in 360 units, and this d is the same. This is still how much we shift this thing up or down by. So don't get confused, or don't worry about the different variables, p, q, and so on. It still means the same thing. This is still amplitude, this is frequency. And what does that mean? If we want to find what q is, we know that q, just like b, is equal to 360 over period. What was period? Period, once again, is equal to the time taken for one, actually I'll write it like this, for one revolution. And remember, t is itself, our input, is measured in minutes. So essentially, in terms of minutes, how long does it take for this hour hand to sweep through a whole revolution? So how many minutes would it take? Well, on a grandfather clock, it needs to pass through, 12 hours. Okay, so it needs to pass through 12 hours, but we're not measuring our units in hours, we're measuring it in minutes. So how many total minutes is that? That means it's 720 minutes. Essentially, how long will it take to sweep through one revolution and get back to our starting point? Well, it will take 12 hours. But we're not measuring in hours, we're measuring in minutes. Each hour has 60 minutes, so overall it will take 720 minutes to get back to our original starting point. And that's what our period is. How long does it take to sweep through one revolution? Okay, so period is itself equal to 720 minutes, which once again we found out by 12 times 60. Okay, so it looks like we're pretty good here. We're well set up. Q is equal to 360 divided by period. 360 divided by 720 is equal to 1/2, or 0.5, which is what we've shown right here. So in terms of process, I'd imagine they would expect you to write 360 over 720 is equal to 0.5, potentially even this formula. Okay, part 2 of question D. Find the value of p. So p here is the coefficient, or the number in front of sine, and even though the representations are different, it still refers to the same thing. It's still the amplitude. Remember, amplitude is the height of the wave, or the distance from the midline to the max point, or the distance from the midline to the lowest point. We had this formula before that we used above for amplitude. It's not given to us in the formula booklet, but here it is. Amplitude is equal to the maximum minus minimum over 2. essentially, what is the distance from the highest point to the lowest point? And then we divide that by 2, and that essentially would tell us the distance from the midline to the max, or it would tell us the height of the wave. So what is the maximum and the minimum value for the hour hand? I think going back to the diagram is actually going to be the easiest way to find these two values. So let's go ahead and do that. Okay. So the dial itself starts at 120 off the ground, and the the hour hand is 10 centimeters in length. So what is the highest point that this hour hand reaches? Well, it's going to reach its highest point. Let's see if we can zoom in a little. It's going to reach its highest point, and it's here. This is going to be 10 centimeters. We know this itself being 30 centimeters. That means half of the dial is going to be another 15 centimeters. Oops. And then, of course, the height of this grandfather clock all the way to the ground is itself equal to 120. So if we can take the sum of this, this would be 120 plus 15 plus 10. This would be 145. That's going to be its max. The max height of the hour hand is equal to 145. So once again, 120 plus 15 is 135, plus 10 is 145. And what's going to be its minimum value? Can go right ahead actually and almost write this out, but here we are. So this is 10 centimeters below, and of course, once again, if this right here is 30 centimeters, this is this line of 15, we are going to be 10 below, which means that there's only going to be, 5 centimeters here. So once again, this is 15 centimeters. If this is 10 right here, then this remaining distance would itself be 5. So what is the distance from the ground? 120 plus 5 right here. So the minimum point that this hour hand reaches is going to be 125. Minimum equals 125. So once again, starts at a base of 120. If it swings all the way down here, we're going to be 10 centimeters below this midline. This midline itself is 15 above 120 or 135. Take away 10 from that, and we're at 125. So max is 145, min is 125. Okay, so if we have that, I think we should be good for the amplitude here. There's our max and min. Let's go ahead and substitute. So we have 145 minus 125 over 2. This is going to be 20 over 2, or just like for the minute hand, it actually equals to the the length of the hand itself. So the hour hand is 10 centimeters, the minute hand was 15 centimeters. The amplitude for each are both the same. Okay, so P, we might say P is equal to 10, but not quite yet. We're not actually done yet. This is fourth question of a paper 2, so it starts to get a little challenging. One thing that we notice, and I hope this isn't too long, just like in the previous example, we had our amplitude, as greater than or equal to 0. We see that that's actually missing here. We don't have P being greater than 0. We say, okay, well, what would it mean for P to be negative, and should it be? We can't just put a value of 10. It's not quite there yet. So let's look at a sine function, and then we'll look at our specific situation. So here is a generic sine function, something like this. Starts at 0, 0, goes to a max of 1, goes to a minimum of -1, and it starts at the origin. Sweeps through 360 degrees. Okay. But if we're talking about our hour hand right here, I'm going to try to draw it, I suppose, just the hour hand. Let's look at this hour hand here. When it starts to spin, or when it starts to rotate, if it travels clockwise, this height, which starts at its midline, just like our sine does, starts at the halfway point at 3 p.m. But when it rotates clockwise, it's actually going to go down. And that's different than what we have here for this generic f of x is equal to sine x. Because normally our sine function actually increases and then decreases. But this function actually decreases and then increases. So what can we do? If our function is supposed to look like this, for example, how can we make that so, I suppose? In this case, how can we reflect it over the x-axis? Well, if we want a positive value to be negative, positive value to be negative, or a negative value to suddenly become positive, what can we do? Well, we can multiply the whole function by a negative. And that's exactly what we'll do here. So instead of having just 10 as the value in which we multiply sine by, we'll multiply it by negative 10. So 10, again, is our amplitude. It's the height of the wave, essentially this 10 centimeters of the hour hand, the height of the wave, the distance from the midline. But for this function, it doesn't actually increase at the beginning, it decreases. So we're going to need to multiply by a negative. All right, so answer in the end is negative 10. Part E. Find the height of the tip of the hour hand above the ground at 4 p.m. Okay, so for this, we've almost created a function. Let's go and maybe just clear some space. Let's look at E right here. What do we have so far? G of t, which tells us the location of the hour hand through time, is given by p sine q of t plus d. We found p was equal to negative 10. We found q itself was equal to 0.5. And then d we actually don't know yet, but it's the midline, the halfway point. So let's go all the way back just really quick, and I think we can work this out fairly quickly. So once again, the midline is just going to be 120 plus the halfway point, 15. So the midline is, what do we shift this up? What is its average? Sometimes it's going to be below, sometimes it's going to be above. The highest and the lowest will cancel out. What would its average be? Well, this halfway point of 120 plus 15, or 135. So our midline, what we shift this function up by, is going to be equal to 135, the halfway point right here. So plus d, which is given by 135. Okay, now we have a function, we just have an input, and we need to find the location of this hour hand at some given time t. All right, so this is a good paper too. There's actually a lot of moving parts here. You can't be too, I suppose, not reckless, but too quick in working through this. So what is our input going to be? We've got our function, it accepts an input of time and will give us the location. But we can't just put in 4. We can't put in 1 hour. Remember, t is the number of minutes after 3 p.m. So how many minutes have elapsed after 3 p.m. till the point of 4 p.m.? Well, it's going to be 1 hour and it's going to be 60 minutes. So in this case, t, our input, should be equal to 60. So we want to find g of 60 essentially. So negative 10 sine 0.5 times 60 plus 135. Okay. Now let's go to the calculator and work this out. So negative 10 sine, then we'll have 0.5 times 60 plus 135. Make sure you're in degrees. And the answer is 130. So we are 130 centimeters above the ground. So let's go back to the document. Answer is 130 centimeters. And that makes sense. We should be lower. So this would be a way to check also if you forgot to put a negative here and you were to input your value of 60 and for some reason it was higher than, let's say, this midline, then that would tell you, maybe something went wrong with this original function. Because of course the hour hand is going to be lower at 4 p.m. All right, let's go on. Part F. Find the first time after 3 p.m. at which the tips of the two hands of the clock are at the same height above the ground. Give your answer correct to the nearest minute. Okay, this is actually not too bad of a question to end off. We have two functions that we've created on the way to this step. We've got g of t, and g of t tells us the height of the hour hand at any particular time. And then earlier, we found out all of these variables right here, which allowed us to essentially write out, if we wanted to, f of t. And f of t tells us the height of the minute hand above the ground at any particular time. And then again, starting after 3 p.m. So essentially, if we want to find the time in which both the height of the minute hand is equal to the height of the hour hand, we should be able to set f of t equal to g of t, because both f of t and g of t tell us the height of each of these respective hands. So let's go and do that. So here we are for f. Oops, just write a normal f, I guess. And what we want to find out is when does f of t equal g of t? So first off, what is f of t? Let's maybe go all the way back here. We found these variables. So here we are. So f of t is equal to, a we found to be 15, b was 6, and d was 135. So a was 15 cos 6t plus 135. So that was f of t. We found that earlier by finding both a, b, and d. 15, 6, 135. So here's f of t. That looks good. And now let's find g of t. G of t, I think we actually found right here. So let's write that out. G of t is equal to negative 10 sine 0.5t plus 135. All right, that's essentially what we wanted to find. When does f of t equal g of t? I guess we don't actually need this right here. Okay, so now we've got an equation. Looks a little unfamiliar potentially, but it's an equation just in terms of one variable, just in terms of t. Let's find the value of t that balances, that makes this true. All right, let's go ahead and work this out on the calculator. We'll n solve, or we could graph it, but I think n solve will be the more straightforward way to do this. So here we are. All right, 15 cos 6t plus 135, and all of this should be equal to negative 10 sine 0.5t plus 135. And you could have subtracted 135 from both sides if we wanted to, and that would have, I guess, cleaned things up just a little, but it doesn't matter so much if we're just going to n solve it in the end. All right, 15 cos 6t plus 135. This looks good. In degrees, and there's our answer. So negative 14. Negative 14 is a problem because t itself should be greater than or equal to 0. So it's not the end of the world or anything. We'll still use this, but we're just going to have to make one qualification. So remember what nsolve does is it finds the value that is closest to 0. So essentially, nsolve will say, okay, sure, I'll find that value of t, and it starts searching, and it starts searching from 0, and it will go left and right, left and right, left and right, until it lands on a value, the value that's closest to 0. In this case, we need t to be greater than or equal to 0, so we need to ask the calculator, let's put a comma 0, we need to ask the calculator to start searching from 0 and then go to the right. Essentially, we set up a lower bound here. And there we go. So 15.8807. So 15.9 minutes. Okay, so let's go back to the document and work this out. T is equal to 15.8807. I'm going to keep all the digits because, looking back at this question, it says give your answer correct to the nearest minute. So find the first time after 3 p.m. Give your answer correct to the nearest minute. That is to say, if we were to look at the clock, what time would it show? It wouldn't show 15.8807. It would show 3, so 3 p.m. plus 15 minutes, and then 0.88. This would be, to the nearest minute, we could imagine this would be approximately equal to 16 minutes. So overall, the clock would show 3:16. I suppose this would be p.m. Okay. There we go. Question 5. Zhu Shen designs a plastic cover in the shape of a cylinder combined with a hemisphere on top, as shown in the diagram. The plastic used to make the cover forms the curved surface of both the hemisphere and the cylinder. There is no bottom to the cover, however it stands on a flat horizontal surface. Let the height of the cylinder be h centimeters and the internal radius of its base be r centimeters. Part A asks us to find an expression for the total internal surface area, a centimeters squared, of the cover in terms of r and h. Alright, so we want to write an expression for A, the total surface area. We don't know any values, so we're just going to have to write it in terms of r and h. So let's write out an equation to kind of get us started, and then we can flesh this out. So here's A, the surface area, and it's given by what? It's composed of the surface area of the cylinder and the surface area of this hemisphere. So if we can go into the formula booklet and we can find the formula for the area of the surface of a cylinder and then the surface area for a hemisphere, then we should be good. So let's go ahead and do that. Geometry and trigonometry. Here it is for our cylinder. So curved surface of a cylinder is given by 2 pi r times h. 2 pi r, remember, is the circumference, and then multiply it by height, and that would give us the surface area. So surface area of a cylinder, 2 pi r h. Let's go back and write that in. So A is equal to 2 pi r h plus, and then what about the surface area of a hemisphere? So going back to the formula booklet, go down just a little more. Here we have the surface area of a sphere. Surface area of a sphere is given by 4 pi r squared. Of course, that would be, that's okay, I suppose. It's a little messy. Maybe I can do better, but this is the surface area of an entire sphere, but we don't have an entire sphere. We just have half of a hemisphere. Or sorry, we have half of a sphere, which is a hemisphere. So we have 4 pi r squared, but we don't have this whole sphere, so we need to divide by 2. 4 over 2, this is just going to simplify to 2, and we'll be left with 2 pi r squared. So once again, surface area of a sphere, 4 pi r squared, we only have half of that, so it's 2 pi r squared. 2 pi r squared is the surface area of a hemisphere. Let's write that out. 2 pi r squared. Okay. And that's it. Part B. Show that the total volume, V centimeters cubed, enclosed by the cover and the horizontal surface is given by the expression v equals 2 pi r cubed plus 3 pi r squared times h all over 3. Okay, so this one looks like it might be, I suppose, a little heavy algebraically, but I think it should be okay. In this case, similar to this surface area question right here, we want to write an expression in terms of volume. So total volume enclosed by the cover and the horizontal surface. So essentially, if we're looking at this cover, which is made up of this hemisphere and this cylinder, what is the total volume that it contains in terms of r and h? After all simplification, it should look like this. So let's go ahead and work that out in a similar way to what we've done here, but this time in terms of volume. So here's volume. Volume, we want to find the volume of a cylinder plus the volume of a hemisphere. And in the end, we should get something like this. So let's go to the formula booklet, find the volume of a cylinder and the volume of a hemisphere. So let's start off with a cylinder again. Here's the volume of a cylinder. It's given by pi r squared times height. So remember, for a prism is something with a uniform cross-section. All we need to find is this cross-section. In this case, it's the area of a circle, pi r squared times height. And that's exactly what our formula is, pi r squared times height. And that would give us the volume of this cylinder. So we know what the volume of a cylinder is. It's pi r squared times height. Pi r squared times height. And what about the volume of a hemisphere? Volume of a hemisphere, moving down a little here. Volume of a sphere is equal to 4 over 3 pi r cubed. It's right here. But once again, we're going to need to divide that by 2. Okay, 4 over 3 pi r cubed, but that's the volume of an entire sphere. We don't have a sphere, we only have half of it. So we're going to need to divide this by 2. So let's go back to the document and we'll work with it there just because I feel there's more space. All right. So here we go. Let's use this space if we can. Volume of a sphere is equal to 4 over 3. This was pi r cubed. We don't have all of this. We only have half of a sphere. So what can we do? We can divide this by 2. That might look a little intimidating. The other way to divide by 2 is to multiply by a half. So you can divide things into 2 parts, or you can multiply by a half and essentially do the same thing. So if we take 4 over 3, we multiply this by a half, 4 over 3, and then of course this is times pi r cubed. What is this going to be? This is going to be, how can we do this? Let's actually just simplify this way. 4 over 2, this is going to simplify to 2. And in this case, we'll have 2 over 3 times pi r cubed, which is the same thing as saying 2 over 3 times pi r cubed over 1. Remember, when we multiply our fractions, we multiply the tops and the bottoms. And then we'll just have, running out of space, we'll just have 2 pi r cubed over 3. Okay. If this step right here was a little confusing, this 1 over 2 times 4 over 3, and you're unsure how we just cross this out, this 2 and this 4 like this, essentially we can use the same practice. Multiply the numerators and the denominators, and this would be 4 over 6, which simplifies to 2 over 3. We can take that step as well, and we'll still get that same answer of 2 over 3 times pi r cubed. And here we have it, 2 pi r cubed over 3. That's the volume of a hemisphere. All right. So we are on our way, but we're not quite there yet. It's supposed to look like this in the end. So here's the volume of a cylinder, volume of a hemisphere. Now we need to group like terms, or essentially create a common denominator and put these all together. All right, so how can we do that? We see that this is written over a 3. So this is a fraction with a denominator of 3. We can write any just plain number, or even this pi r squared times h. We can write this as pi r squared times h over 1. And then the question is, okay, now we've got two fractions, technically speaking. And how can we get the denominators the same? This one's over 3, this one's over 1. So what we're going to need to do is we're going to need to multiply this denominator by 3 to make it the same. We can't just do that to the bottom, we need to do it to the top and the bottom. That is to say, we need to multiply both the top and the bottom by 3 to get a common denominator. So let's do that. Multiply the top and the bottom by 3. Okay. So now we'll have 3 pi r squared times h over 3 plus 2 pi r cubed over 3. And now, since they're both over a common denominator, we can just add the numerators. That would be something like this, for example. Like if you had 1 over 7 plus 2 over 7, altogether you have, well, 3 sevenths. You can use that same principle even in this abstract context. So all we'll have is 3 pi r squared h plus 2 pi r squared all over 3. And that's exactly what we have here. 2 pi r, whoops, this should be a cubed. There we go. 2 pi r cubed plus 3 pi r squared h, 3 pi r squared h over 3. If we wanted to, in the end, we could switch these around. A plus b is equal to b plus a. Order doesn't matter when we add like this. Okay, so there we go. That is our proof, I suppose, or that is us showing that the volume can be expressed in this way. Okay, I'm going to clear some of this up. The total volume enclosed by the cover is 10,000 cubic centimeters. Hence, show that h equals 30,000 minus 2 pi r cubed over 3 pi r squared. Okay, so we know the volume. This is actually, to be honest, just an algebra-heavy question. It's a rearranging question. We know the volume is equal to 10,000 centimeters cubed. Here's an equation where we link volume to the radius and the height. In the end, we are going to want to substitute this value of 10,000 in for v, and out of all of this, we want to rearrange it so we get h all by itself. So this is still an equation in terms of h and r. When we substitute 10,000 in here, we're going to have an equation in terms of h and r. But what we're going to want to do is get h all by itself. Seems a little daunting, but let's check it out. Okay. So let's substitute 10,000 in for volume. And of course, always maximize process marks. Substituting just 10,000 in for volume might be enough for process marks. I'm actually going to, we'll look at the mark scheme at the end. So volume is equal to 10,000. Now we have 2 pi r cubed plus 3 pi r squared h all over 3. And what I'm going to do is I'm going to bring this down a little because I think we're going to need more room. So we substituted in for volume of 10,000. And now what we want to do is get h all by itself. So we want to rearrange this and get h all by itself. We want to free h, essentially, make it the subject. All right, so all of this is being divided by 3. Order of operations tells us that we can't just like move this over. We need to get rid of this 3 because all of this on the top is being divided by 3. So if we want to undo and peel off the layers in some sense, we're first going to need to get rid of this 3. Everything's being divided by 3. Inverse operation tells us, okay, well, if everything is being divided by 3, how can we undo this? Well, we can multiply by 3. So let's multiply by 3, and then we can get rid of this divide by 3. What is the opposite operation? So multiply not just one side by 3, we're going to need to multiply both sides by 3. Remember, when we're dealing with balancing equations, it's essentially like a scale. You can multiply both sides by 3 and it still balances, but if you just multiply one side by 3, then of course, well, it's no longer balanced. It might be heavier or lighter on one side. So let's keep going. So since we multiplied this by 3, 3 over 3, 3 divided by 3 is going to cancel. Right? That was our point of doing this. 3 divided by 3 is just equal to 1, so we get rid of the division by 3. And now we have something like this. 2 pi r cubed plus 3 pi r squared times h, and then 3 times 10,000 is 30,000. Okay. So what's the next step in getting h all by itself? Well, we don't really need this on this side. We want h, just h alone. So let's move this to the other side. So the trick with moving something to the other side, we just change its sign. Really what we're doing essentially is we are taking away 2 pi r cubed, and here we're going to take away 2 pi r cubed. Once again, going back to this idea of a scale, we're lifting up essentially a 2 pi r cubed from this side and a 2 pi r cubed from this side. It's going to balance still. So what does that look like? 2 pi r cubed minus 2 pi r cubed, that's just going to go all the way to 0. And on this side we'll have 30,000 minus 2 pi r cubed equals 3 pi r squared times h. Okay, we're getting a little closer to getting h all by itself, but h is still being multiplied by this 3 pi r squared. So we have h multiplied by 3 pi r squared. We just want h by itself. So how can we get rid of this 3 pi r squared? Well, it's currently multiplied by h. So what we can do is we can actually divide it away. So we'll divide both sides by 3 pi r squared. Let's divide this side as well by 3 pi r squared. Anything divided by itself is just equal to 1. So 3 pi r squared divided by 3 pi r squared is just equal to 1. Now we have 1 times h, which is just h. And we'll have 30,000 minus 2 pi r cubed over 3 pi r squared. And I think, I've actually forgot what it looks like, but here it is. 30,000 minus 2 pi r cubed over 3 pi r squared. 30,000 minus 2 pi r cubed over 3 pi r squared. And now we've got h by itself just through some, to be honest, some rearrangement, I suppose. Okay, let's keep going. So actually, sorry, we said we would look at the mark scheme. So part C, right here. So this is good. This is a 2-mark question, and it was quite involved, to be honest, in terms of the arrangement. 10,000 substituted into B, correct rearrangement with at least one line of intermediate working leading to the given value. And then here is the answer, which they had already given to us. So it looks like substituting 10,000 in for volume will allow you to split this, which is, I think, fairly good. There's some, fairly involved rearrangement, but just substituting 10,000 will allow you to split this final question of a paper 2. So always maximize process marks where you can. Okay. Duchenne uses the total internal surface area to model the amount of plastic used to construct the cover. Show that A is given by the expression A is equal to 2 pi r squared over 3 plus 20,000 over r. So what does A refer to again? They're telling us it refers to the internal surface area, or the total internal surface area. And that's what we actually found out here as well. A is the total internal surface area. Earlier on in this very first question, we wrote out an equation for the surface area. And let's actually copy this right here. And we'll compare it to the equation below. So here we see an equation linking surface area to r, and only r, whereas our original equation, we had surface area in terms of both r and h. So the difference is we somehow managed to get rid of this h. You can ask, well, how did we do that? Well, above, in this previous question, in C, we had h linked to r, or h is equal to some equation, some value in terms of r. Essentially, we have h expressed in terms of r. So if we want to get rid of this h here, what we can do is we can replace this h right here, since h equals to all of this business in terms of r, we can actually just substitute this h into this equation, and now wherever we have an h, we'll have, well, this whole, kind of looks like a mess to be honest, but this whole business in terms of r. And that's going to be the strategy. So once again, here's surface area in terms of r, here's surface area in terms of r and h. Here we have something where h is equal to a whole expression in terms of r. So what we can do is if h is equal to all of this expression in terms of r, we should be able to just substitute into here, and now we'll have something just in terms of r. We'll manage to get rid of the h through substitution. All right. So this might be a little heavy in terms of algebra, but we're going to need to substitute and then simplify. So I'm going to actually get this onto another page and then try to work this out. So once again, here is our original expression or equation for surface area in terms of r and h. Here's h in terms of r. Let's substitute into here, and then we'll just get this in terms of r. All right, so is equal to 2 pi r. Now wherever we see an h, we'll write out 30,000 minus 2 pi r cubed over 3 pi r squared plus 2 pi r, 2 pi r squared. All right, so remember this equals is the same as is. It's essentially what it means. So h is all of this business. Wherever we see an h, we can replace it with this in terms of r. Now we've just got something in terms of r. I would say this as well. There's going to be a fair bit of algebra involved from this point on. It's a 2-mark question on a timed test, if you have the time, of course, but you may have to ask yourself, in some ways, in terms of the distribution of marks, just this substitution already allows you to split this question. Now, if you've done everything and you're just going on, or if you're confident that you have enough time, then of course, work through it. But splitting this question is just substituting in, already allows you to get one of the 2 marks. And, well, now is the algebraic manipulation to show that this right here is equal to this, and it's somewhat involved. So I'm going to work through it, and I'll just speak through as I work through this. So here we have 2 pi r multiplied by all this business, and then there's plus 2 pi r squared at the end. I'm going to create a fraction because we have these 2 things being multiplied by each other. After that, just looking at these, we have a pi in the numerator and a pi in the denominator, and an r squared. So let's simplify. Pi over pi is anything divided by itself is 1. We also have an r in the numerator and an r squared in the denominator. So I'm going to cancel out an r, and one of those r's is going to go here. So it's not r squared anymore, it's just an r. So writing this out, we have 2 times 30,000 minus 2 pi r cubed. And on the bottom we have 1 times 3 times r, which is just going to be 3r. And then we have 2 pi r squared. We have a fraction here, but we don't have a fraction here. Let's make it into a fraction by writing it out over 1. Now we see we don't have the same denominators. Let's create a common denominator here by multiplying both the top and the bottom by 3r. All right. Now, let's rewrite this. 2 times 30,000 minus 2 pi r cubed. And then this is going to be all over 3r. And now this is going to be, grouping like terms, we have, let me use a different color, 2 times 3 is going to give us 6 pi. R squared is r times r, and then times another r. It's going to be 6 pi r cubed. And then it's over 3r. Okay. We've got common denominators, so we can write the numerator. We can just add the numerator, essentially. 30,000 minus 2 pi r cubed plus 6 pi r cubed. And once again, this is all over 3r. Now it looks like we're going to need to expand. I'm going to go back up and check. Yes, it looks like we are. Okay, let's go ahead and expand right here. So we use, some of you might know this as the rainbow method. 2 times 30,000 is going to be equal to, actually I think we could factor here as well, but let's maybe just expand and then factor. That's going to be okay as well. 60,000 minus 4 pi r cubed plus 6 pi r cubed all over 3r. Here we have 4 pi r cubed, or minus 4 pi r cubed. This is 6 pi r cubed. So it might look a little funny, but imagine that you have 6 pi r cubed. Someone comes along and they take 4 pi r cubes away from you. Now you only have 2 pi r cubes. So what is this? This is 2 pi r cubed plus 60,000 over 3r. And we are almost there. But now what they want us to do is split this 3r into 2 terms. So essentially break it up again. Just like we grouped these like terms, or sorry, when we had a common denominator, we could add the numerators. We can actually split this and kind of reverse the process by writing 2 pi r cubed over 3r plus 60,000 over 3r. And now let's simplify again. Here we have an r on the bottom, and that will reduce this r cubed just to r squared. 2 pi r squared over 3. Now let's do this as well. We have 60,000 divided by 3. That means this is going to go to 20,000. And we'll have 20,000 over r. And I really hope that this is the same here. There it is. Okay. 2 pi r squared over 3 plus 20,000 over r. To be honest, that was quite involved. And on a timed test, I wonder, just going from 1 mark a minute, I would be a little cautious. I think that's almost like a time trap in some ways. I'm not sure. I don't think the IB deliberately puts something on like this as like a time trap. But in terms of the distribution of marks, there's 2 marks for this. Substituting h into this is already 1 mark, and all of this business is just another mark. So I'm not sure. It's a lot of work for 1 mark. Okay. All right, let's keep going. All right, last part. Continuing on, this is rounding out the question, I guess. Chu Shen wants to use the minimum amount of plastic in the construction of the cover. Find an expression for dA dr. So dA dr is the derivative of A. So what was A? We actually worked it out here, but they also gave it to us here as well. So here is A is equal to 2 pi r squared over 3 plus 20,000 over r. So let's actually copy paste this, and then let's find the derivative of this. That's what they're asking us to do. So here's A. Now let's find dA dr. All right, so first thing, just looking at this, since we want to take the derivative, we have this variable in the denominator. And this is essentially what you would kind of expect on a last question of a paper 2. Often it is some challenging calculus, and there's going to be a lot of moving parts. So here we have a variable in the denominator. Remember, if we had something like this, like f of x is equal to 1 over x, and we're suddenly asked to take the derivative, we can't just go right away and find this 1 over x. We first need to write it as x to the negative 1. Or if it's 1 over x squared, we need to write this as x to the negative 2, or in general, 1 over x to the n is just x to the negative n. Whatever we're raising this to the power of, we need to move it up essentially. Just move this exponent up and write it as a negative. Move this exponent up and then write it as a negative. That's maybe the kind of heuristic, or the memory kind of trick, I guess. Okay, so let's first rewrite this actually. So let's not write dA, dr yet. Let's write this in a way that allows us to treat it with this variable in the denominator. So 2 pi r squared over 3 can stay as it is, but here we'll have 20,000, and then 1 over r. Essentially this is the same as 20,000 times 1 over r, which is going to be 20,000 times r to the negative 1. Remember, just move it up and then we'll have a negative exponent. So r to the 1 at the bottom just becomes r to the negative 1. So this is going to become 20,000 r to the negative 1. Now we're in a position to take the derivative, dA dr. All right. Here is our power rule. F of x is equal to x to the n. F prime of x, take that power of n, whatever it is, whatever the exponent is, multiply it out in front, and then whatever that exponent was, just take 1 away from it. Okay, and then I guess I would just say one last thing. F prime of x is equal to dy dx. Oops, a little messy, but there we go. So this dA dr is essentially just a prime, I guess we could also say. If we wanted to, we could write it as a prime. They mean the same thing. Take the derivative of a. All right, let's go ahead and work this out. Derivative is just in terms of r. This pi is not a variable, it's a number, so we don't have to worry about it. So let's take this 2, multiply it out in front. So now we had 2 pi over 3, but now we're multiplying all of that. So now it's going to be 2 times 2 is 4. 4 pi, still going to be over 3. And I guess we'll have this r. R used to be 2, we take 1 away from it, now it's only 1. Now let's go to the second term right here. What are we going to do? Let's take this negative 1, multiply it out in front. So negative 1 times 20,000 is now negative 20,000. R used to be negative 1. Take 1 away from that. Now it's negative 2. Okay. And that's it. So find an expression for dA dr. There it is. 4 pi r over 3 minus 20,000 r to the negative 2. Okay. Find the value of r and the value of h that minimizes the use of plastic. Okay. So this is a 4-mark question, and I think there's actually a little ambiguity here. Usually you would expect a question like this to say hence. Hence requires you to use what has come before. In that case, we would have had to say, okay, where is this function? That is to say, the surface area minimized for what value of r. In that case, we would use the derivative and set the derivative equal to 0. I'm not sure if this is a more familiar concept, but maybe I'll just draw a quick sketch. This isn't too much, too kind of involved, but let's just take a simple quadratic, for example. Remember, a derivative tells you the slope at any given point. So here's a positive slope, here's a slightly less positive slope, here's a negative slope, and so on. If we want to find the maximum point, and then let's just write this as y and x. The maximum is going to occur when we are done rising. So here, increasing, 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 decreasing, decreasing, but there's going to be a point where we have a slope equal to 0. That is to say, where dy dx is equal to 0. That's going to give us a maximum. So in this case, or I guess conversely we could say a situation where we have similarly a minimum. Dy dx is equal to 0. After we are done all of the, I guess, decreasing that we're going to do, before we start increasing, there's going to be a point where we reach the lowest point. So setting the derivative equal to 0 is how we can find a maximum or a minimum. So when they ask us to find a value of r that minimizes the use of plastic, what they're asking us, if it said hence, would be to set dA equal to dr, or dA dr equal to 0, and then solve. That might actually be the easiest way to actually work this out in the end. So we can use that, and I'll show you another method as well. So here's our derivative, dA dr, change in surface area as a function of change in the radius is equal to all of this. But when is the slope equal to 0? When has it reached its lowest point before it starts increasing again? It's going to be when dA dr is equal to 0. So let's go ahead, substitute dA dr for 0, and then we'll solve. 0 is equal to 4 pi r over 3 minus 20,000 r minus 2. And I think we can graph it, but this is going to be very big and it's going to suggest that we're going to need to change our window. So let's actually end solve this. So here we go. Menu, algebra, numerical solve, and let's go 4 pi r. 4 pi r over 3 minus 20,000 r to the negative 2. And we want all of this to equal 0. And let's ask the calculator to solve for r. Okay, so when r is equal to 16.8389, or 16.8. Let's go back to the document. So when r is equal to 16.8, actually that's right, 389 centimeters, this function has a minimum surface area. Okay. Now, we also need to find the value of h. So we know what r is. Now, is there a situation where we have r linked to h? There is. Right up here, we have r linked to h. So I'm actually just going to copy this here. And what we'll do is we'll substitute the value of r that we found into this equation, and that should allow us to find h. So let's do that. So what is h equal to? 30,000 minus 2 pi, and then this is, I'm going to keep all the decimal places. Usually you want to round to 3 significant figures only at the end of a question. So let's keep as much accuracy as we can. 16.8389 squared. Okay, let's go ahead and go back into the calculator and work this out. So set up a fraction, 30,000 minus 2 pi, and then r. Might be nice to actually just copy paste this to get all of the decimals, but I don't know if you would have that chance on actual exam or using your handhelds. So let's just use what we have here. 8389. 16.8389. And we want to cube this value. And then here we have 3 pi. And it's going to be multiplied by, once again, 8389. And here we want to square this. Okay. Whoops. Okay, so there it is. It is very, 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 very insignificant. And what I'm guessing is if we were to use the full accuracy here, this would go all the way to 0. So once again, here's this value of r that we found initially. This is the radius of the hemisphere. This is the value that minimizes the surface area while maximizing the volume. And with this value of r, what is h? We had h equal to all of this right here. When we substituted that value in for r, we found out that h was like super, super, super insignificant. And by the looks of it, it could just be, well, likely is just due to accuracy itself, that we haven't used the full range of accuracy here. If we did, the assumption is that this h would go to 0, and that is to say we should have no cylinder at all. So this is a value of r that minimizes surface area and maximizes volume. What is the corresponding value of h? That is to say the height of our cylinder. Well, the height of the cylinder is actually 0, which suggests that we shouldn't even have a cylinder. If we want to just maximize the total volume and minimize the surface area, we should just use the hemisphere and then get rid of or not use the cylinder. So, what is the value of h? H is equal to 0. Let's go back to the document and write that out. H is equal to 0. So these are our two values. So in this case, r is equal to 16.8389 and h is equal to 0. So here are the values for r and h that minimize the use of plastic. And here part G says, by interpreting your answer to part F, suggest the best shape for Jushen's plastic cover. So the best shape is, as we mentioned earlier, is just going to be a hemisphere. That is to say, keep the radius, but the height of the cylinder goes to 0, which essentially means we have no cylinder. If we want to minimize the amount of plastic and create some cover, we should just actually keep the hemisphere and not use the cylinder at all. So, interpret your answer to part F. The best shape. The best shape is a hemisphere. And I suppose, just to make it clear, we could say hemisphere only. All right. So that was that. That was, I think, a pretty challenging question to end off. It was a good paper too, that's for sure. And I hope it was helpful. And as always, best of luck.